Hello everyone. Today we're going to talk about optics. This is the first video about optics. In the beginning, it was the Big Bang from which the universe was formed, right? It was the birth of everything that exists. Not entirely sure if that was the first time things came into existence. If you believe in a cyclical universe, then the Big Bang was just another beginning. After the Big Bang, the cosmic unified forces separated into the four forces present in the universe today. These are the gravitational force, causing masses to attract other masses, electromagnetic force, giving charge to particles, the weak force, which breaks the nucleus of atoms, and the strong force, which keeps the nucleus of atoms together. Everything then began at the Big Bang. All things have a single common origin. So at the moment of for the Big Bang, at the singularity, all the four forces were unified into a single force. That brings to mind that given enough density, pressure, and temperature, all forces become one, and everything has a common origin. But the goal of this video is to talk about optics, but I'm just giving a brief summary introduction on the nature of light, for example. Light is responsible for the electromagnetic force, the weak force, and the strong force, and who knows, maybe there's a relationship between light and gravity. The electric force between particles is kQq over r squared, as I explained in other videos, where k is the Coulomb's constant. The two q's are the two charges or charge objects, and r the distance between their center. Light is an electromagnetic wave. The electromagnetic fields are always 90 degrees from each other. So if you see a beam of light, it has an electric field 90 degrees to the magnetic field, but one is bigger than the other. The electric field is 3 times 10 to the 8 times bigger than magnetic field. Isaac Newton discovered that color white is composed of all the colors of the rainbow. These colors can be broken and when white light is passed through a prism. So in the same way that all forces came from a single force at the singularity at the moment of the Big Bang, all colors of light, when put together, they add up to the color white. Electric field lines are field of photons emanating from particles. The field lines point towards the negative charges and away from positive charges. So the electric field lines are a field of photons, and these photons mediate the forces of electromagnetism, weak and strong. These are the electric field lines between the opposite charge particles. The force between them is attractive. When you have two opposite charges, one positive, one negative, they attract each other, and the field lines look as in the image. And when you have two charges that are positive or two charges that are negative, the electric field lines avoid each other and there's a repulsion. Light. What distinguishes one form of light from the other is its wavelength and frequency. Everything is actually light, right? Even our brain activity can be mapped through waves. And if string theory is correct, then everything are just a bunch of strings vibrating, which brings to mind that everything could possibly be a form of light, a form of energy. So here we got the spectrum of light, and the color that is most energetic is violet, then comes blue, green, yellow, orange, and red, the least energetic. But these are the visible spectrum. We also have the parts of the spectrum that we cannot see with our eyes, which is gamma rays, X-rays, UV, infrared, and microwave, and radio waves at last. Well, we cannot see those, but they're present, and we can detect those with our devices, with our technology. Okay, we have two types of mirrors. We have concave mirrors and convex mirrors. Like I said before, light is an electromagnetic wave. The electric field is equal to 3 times 10 to the 8 times the magnetic field being 3 times 10 to the 8 the speed of light. And as you see in the equation, the speed of light is equal to 1 over the square root of these two constants, permeability of free space and permissivity of free space. Light reflects off surfaces at the same angle as the incident angle. So when there's a reflection, when a light ray is going towards a surface, it reflects at the same angle that it comes in, and the angle is measured from the normal line, which is a line perpendicular to the surface. Okay, now let's see. So now the next part is that um, we have our concave mirror. So when light from infinity arrives at a concave mirror, it focuses at the focal length. It converges in front of a mirror. Focal length is positive and real when it does that. The image can be positive, real, or negative virtual, depending how far away the object is from the mirror and so forth. Convex mirrors, however, converges light behind the mirror. So if you if you think of an imaginary line going from the ray to behind the mirror, so it's almost like as if the focal length is behind the mirror, not in front like on a concave mirror. So light converges light behind the mirror, focal length is negative, virtual, image is always negative and virtual. So one thing to remember here is if light, if the image or the focal length is behind the mirror on a convex mirror, the image is negative or the focal length is negative. So for a convex mirror, it's always negative because the image will always be virtual and the focal length will always be virtual. On a concave mirror, however, the image can be positive real or negative virtual, depending on the distance between the image, the object, and the mirror. So the equation for mirrors and lenses is the following. 1 over object's distance plus 1 over image's distance equals to 1 over focal length. The image and focal length can be negative or positive depending if they are virtual or real. If they are virtual, the image is negative. If they are real, the image is positive. In the equation, of course. The object is always positive because there's no way that the object can be behind a mirror. So we can neglect the object. But yeah, so if it's virtual, it's negative. If it's real, it's positive. It's virtual if it's behind a mirror. Simply put, depending on what we're talking about as well, right? The focal length is where light from infinity converges. Mirrors and lenses are a way to see the structure that holds the universe together. The cosmos, despite chaotic, has an order. So let's talk about concave mirrors. C is the center of curvature, which is 2 times the focal length. In this first case, image is real, inverted, and smaller. Usually when image is real, it's upside down. In the second case, image is inverted as well. It's real, but it's the same size. How do we know it's the same size? Because it's located at the same place as the object, at the distance equal to 2 times the focal length, right at this curvature. The further away the image is from the mirror, the bigger it is. In this case, the image is just as far away as the object, so their sizes are the same. On this third case, the image is real, as we can see because it's upside down, inverted because it's real, and bigger because it's further away from the object. Notice that it's beyond C, so it's further away from the mirror as the object. Object is labeled as O, and the image is labeled as I. On the fourth case, there's no image because if you put the object at the focal length, the rays of light don't converge at any point, and there's no image. And if then it flips because after you bring the object closer to the mirror than the focal length, the image is now virtual, does it's upside right side up, it's not upside down anymore, and it's bigger. It's behind a mirror, so it's virtual, and because it's virtual, it's going to be negative. Glass is an invention in optics. With optics, you can see the universe. O stands for object location, and I for the image location. Now, let's talk about let, let's talk about the convex mirrors. Well, we only have one case because all images are virtual because they're right side up and they're smaller. So there's not much into that because all images are virtual and smaller. How do we know they're virtual? First thing, the image is not upside down, it's right side up, and it's behind the mirror as you can see on the image. Now let's talk about lenses. We got concave and convex lenses. Concave lenses is when the focal length is negative and virtual. So the focal length of a concave lens is always negative. And because it's negative, it's virtual. So when light comes in at the for infinity, it diverges from the lens. And because it diverges, if you follow the image back to where it converges, it actually has it as a point source behind the lens. Thus, the image is virtual and negative. Convex lens, the image comes from infinity, converges at a single point, focal length is always positive. Now here we got the cases for the convex lens. If the object is further away from C, from the curvature of the lens, the image will be focused between the focal length and C. Because the image is closer to the lens than the object, the image is smaller, and because it's upside down, it's real. On the second case, when the object is right at C, the image is also right at C, so it has the same size and it's real. How do we know it's real? It's upside down. It's always good for y'all to notice the pattern of following the light rays. I always use 3 light rays for lenses and 2 light rays for mirrors. On the third case, we have that the object is between C and F, and the image is further away from C than C. This means that the image is real, but now it's getting bigger. So whenever the object is beyond C, the image is smaller. When the object is placed between C and F, then the image starts getting bigger. Now, of course, if you place the object right at the focal length, there's no image. And if you place the object between the focal length and the lens, the image now is right side up, and it's virtual because it's behind the lens, just like I said before, and it's bigger. So the convex lens, the image can be bigger, no image, same size, or smaller. Waves in the cosmos can be made to converge and diverge. Now, for a concave lens, the image is always virtual and smaller. No matter where you place the object in front of the lens, the image is always virtual and smaller. And if the image is virtual, it's right side up and it's negative. The magnification of the image is negative times the image location over the object. The magnification will be positive if the image is virtual, because if the image is virtual, the image is negative, and negative times a negative gives you a positive. And this same pattern obeys the height of the image. The ratio of height of image over height of object is equal to the ratio of image location, distance from the lens or from the mirror, over the object locations from the lens or from the mirror. It's always from the lens or from the mirror that this distance is measured. And from there, you get magnification. If the image is virtual, magnification is positive. If the image is real, magnification is negative. Magnification is positive if the image is virtual. If the image is virtual, it's right side up. If the image is real, it's upside down and its magnification is negative. Okay, and then there's a little bit of a comment that when light goes through two slits, it causes an interference in the screen after the two slits. Constructive interference causes the visible light patches that are followed by destructive interference that are the dark patches. We're going to talk more about this later, um, about interference and stuff like that. This is the topic for next video on optics here, Optics Xhyn. Now let's talk about the critical angle. When a ray of light travels between a material of higher index of refraction towards a material with lower index of refraction, it can undergo reflection because if it's going from higher index of refraction to lower, the light ray tends to shift away from the normal when it's in the lower end. There is actually a critical angle from the normal in which any angle larger than it, the angle of incidence, there's a total internal reflection, and any angle smaller than it, and there's just a regular refraction. So here we have an example where the angle is just fine, so the light goes through the interface between the two materials. On the second case, it's the critical angle because it's an angle of incidence where light reflects or refracts 90 degrees, completely horizontal. And any angle bigger than that, and the light will reflect. So the equation for critical angle is n1 sine theta c equals n2 times sine of 90. Because 90 is, sine of 90 is 1, so the equation is just that, and of course, and so forth. So this is a summary about the first video on optics. Um, and as you can see, went over briefly about lenses, mirrors, and we finish here with the critical angle. And there's going to be another video to explain about the, the double slit experiment, interference of light, and so forth. See you there. Hello everyone, today we're going to talk about the second video on optics here at Xhyn Physics and Hobby. We're going to talk about interference. When a beam of monochromatic light, which means light of same wavelength and frequency in its entirety, is shot at two narrow slits or at a single slit, or it can also be multiple slits. An interference pattern is formed on the screen behind the slits. The interference pattern is a clear proof the light is a wave. Each slit becomes a source of light which diffracts and interferes with light from other slits, causing regions of destructive and constructive interference. For a single slit, the interference can still happen when light from different regions within the single slit also diffracts and interferes. So when light hits two slits or one slits or multiple slits, each slit becomes a source of light. And if you place a screen behind the slits, an interference pattern will appear because in the screen, each point on the screen will be at a different distance from the slits as other points. And this distance can cause constructive, destructive interference. When light moves from the slits to the screen, behind the slits, and it interferes. When lights from different slits meet at the screen while being whole wavelengths apart, there is a constructive interference. When lights from different slits meet at the screen while being half wavelength apart, there's a destructive interference. So, there is a pattern of constructive and destructive interference. At different points along the screen, light will travel at different distances. So two different rays of light will interfere constructively or destructively, depending if they are whole wavelengths apart or half wavelengths apart. If they are whole wavelengths apart, there will be a constructive interference. If they are half wavelengths apart, there is a destructive interference, such as an example shown. Um, so the equations that describe this phenomenon are shown on the screen. For a single slit, because there's also a thing called single slit diffraction. And in another video, we're going to talk about multiple slits diffraction. More than two, I mean. So for a single slit, when light goes from a single slit, it undergoes interference. The interference shows a pattern of constructive bright spots and destructive interference dark spots. The angle from the center of the screen to where there is the first minimum or region of destructive interference obeys the following equation, where lambda is the wavelength of light and b the width of the slit. So the more narrow the slits, the more widespread is the interference. The more wider the slit, the more the interference will tend to spread less, will also be more narrow. Now, single slit diffraction happens also at double slit diffraction interference, as I'm going to explain a little bit. So for the double slit diffraction, the distance from the center of the screen to the first bright spot, where there is the first maximum or region of constructive interference, it obeys the following equation, where lambda is the wavelength of light, d the distance between the slits, the lowercase d is the distance between the slits, capital D is the distance to the screen, and S is the distance between the central maximum and the first maximum. For the single slit diffraction interference, the theta there is the angle between the center maximum and the first minimum. So for single slit diffraction interference, we calculate when will the minimums be located, at what angles from the center. Whereas for double slit diffraction and interference, the S is the distance between the bright spots. Diffraction grading. So when light goes through several slits, it obeys the equation, as shown, where the slits per meter is 1 over d. N is the order of the spectrum, and d is the slit separation. The single slit diffraction equation indicates regions where the bright spots go missing in the grading spectrum at that specific angle theta. So for several slits interference, the center, the constructive interference towards the center of the screen will be brighter, and as you move outward, it gets dimmer and dimmer. That's because the longer the distance, the lower the intensity of light. But notice that at angle theta, there's a bright spot missing on both sides. That bright spot that goes missing, it can be calculated from how wide the slits are. Doesn't matter if it's one slit, two slits, or several slits. All it matters is how wide the slits are, and that will determine the bright spot that will go missing. And then the center of the screen is where we have the width of the central maximum, which is between the two bright spots that go missing. The intensity of the bright spots lowers the further from the screen, the center of the screen, as you can see there. So in other videos, I'm going to explain more about interference, diffraction, and the wave-particle duality. So for now, this is enough, and I'll see you next time.